Hey everyone, today we're going to talk about section 4.6. This is going to be on some applications of exponential functions. So the first thing that we're going to talk about is radioactive decay. Uh, and specifically half-life. We've actually talked about radioactive decay before, but we haven't necessarily talked about this idea of half-life. So the big idea here is that the half-life of a radioactive isotope is the time that it takes for half the substance to decay. If we are given the basic exponential or growth equation, h of t equals a times b to the t power, half-life can be found by solving for when half of the original amount remains. Here, let me make this a little bit larger for us. And most elegantly here, we actually have 1/2 equals b to the t. That's going to be the equation that we use here, because the amount of substance that we start with actually is completely irrelevant to these problems. 1/2 equals b to the t is going to be the equation that we use here. Let's look at an example. Bismuth-210 is an isotope that decays by about 13% each day. What's the half-life of bismuth-210? Well, if bismuth-210 decays by 13% each day, then let's see, my daily decay rate is 13% or 0.13. So remember, I know that B is 1 plus R. We've discussed this previously. So it means that B is 1 minus 0.13, which is 0.87. So B is 0.87. Now I know that 1/2 equals B to the T power, right? This is my half-life equation. This means that 1/2 equals 0.87 to the T power. Whenever I solve for T, I will have found how long it takes for only half of the substance to remain. So here we have to take a logarithm of both sides. Let's try the natural logarithm. It's my favorite. You can use any logarithm that you like. This gives us natural log of 1/2 is equal to t times natural log of 0.87. And then solving for t, I just divide both sides by natural log of 0.87. And I get t equals natural log of 1/2 divided by natural log of 0.87. And this is about 4.977. This tells me that the half-life of bismuth-210 is approximately 5 days, right? This next question is more of a conceptual question. This is just regarding what half-life is, essentially. So, cesium-137 has a half-life of about 30 years. If you begin with 200 milligrams of cesium-137, how much of it will remain after 30 years? How much of this will remain after 60 years or after 90 years? Well, after 30 years, half of it will remain, right? Because it has a half-life of 30 years. So after 30 years, or maybe we'll say t equals 30 years. We have 100 milligrams left, right? And t equals 60 years. That's another 30 years after the first 30 years. So once again, the substance halves. We'll have 50 milligrams left. At t equals 90 years, once again, the amount of substance that we have will have halved. We will have 25 milligrams left after 90 years. So if cesium-137 has a half-life of about 30 years, which we just established, find the annual decay rate. Okay, so I want to find this rate of decay, right? Previously, so we said 1/2 equals b to the t. I know that b is 1 plus r. Well, what we want to solve for actually is r. In this, I want to find this decay rate. So 1/2 equals 1 plus r to the t. And actually, t is 30 in this case, right? Because this has a half-life of 30 years. This means that 1/2 equals 1 plus r to the 30th. And now we can take the 30th root of both sides, or alternatively raise both sides to the 1/30th power. To get that 1 plus r is equal to, let's see, thirtieth root of 1/2. I'm getting 0.9772. It's about 0.9772. Subtracting 1 from both sides, I get that r is about negative 0.0228, or the annual decay rate is about 2.28%, right? This is, we no longer put a negative sign with this whenever I use the word decay, right? The word decay implies that this would be negative in a math problem. And let's look at another example. Carbon-14 is a radioactive isotope that is present in organic materials and is commonly used for dating historical artifacts. Carbon-14 has a half-life of 5,730 years. If a bone fragment is found that contains 20% of its original carbon-14, how old is the bone? So in order to find out how old this bone is, we first have to find an equation for the decay of the carbon-14. We could use either a continuous or an annual decay formula, but we're going to use the continuous decay formula because it's more common in scientific texts to use a continuous decay formula. The half-life tells us that after 5,730 years, that half of the original substance remains, or that, let's say A is the amount of the original substance I have, right? So 1/2 times A is equal to A times E to the RT, which is 5730. This is just my continuous growth rate formula previously, right? Obviously, since I have an A on both sides, this ends up just being 1/2 equals E to the R times 5730. If I take the natural log of both sides here, maybe as a side note, just remember that natural log of E is 1. So taking the natural log of both sides, I get natural log of 1/2 equals, let's see, 5730r times natural log of e, right? Natural log of e is 1, so it actually goes away. This gives me that natural log of 1/2 equals 5730r. And it goes away because anything times 1 is itself. This gives me that r is natural log of 1/2 over 5730. And this is about negative 0.000121. So my decay is going to follow the equation. Let's see, have I assigned a variable here? No. This is going to follow an equation, we'll say q of t is equal to a times e to the negative 0.000121 t. To find out how old the bone fragment is that contains 20% of its original amount, I just plug in 20% times a, which is 0.2 times a, equals this equation. Notice again these a's will go away. Taking the natural log of both sides, I get natural log of 0.2 equals negative 0.000121 t times natural log of e. So natural log of e is 1, and anything times 1 is itself. And I solve for t by dividing both sides by negative 0.000121. To get that t is natural log of 0.2 divided by negative 0.000121. And this gives us about 13,301 years. This is about how old that bone fragment is. And this is it for the half-life portion of this lesson.